Hi class, our next little video is about the Coriolis effect, which is an apparent force that wind currents and ocean currents experience because of the rotation of the Earth. So it's caused by the rotation of the Earth, and it's a deflection. It's an apparent deflection of moving objects when they're viewed in this rotating reference frame. So it's really only noticeable for motions that are occurring over large distances and long periods of time. So you hear people talk about, oh, when you go to the southern hemisphere, if you go to New Zealand and you flush the toilet, it spins in the opposite direction. That's actually a fallacy, because the scale of a toilet bowl flushing is far too small for the Coriolis effect to actually have any impact. So we're talking about motions of, ocean currents that are flowing on a continental scale, and our big wind currents, our big wind currents that are flowing over large distances and long periods of time. So the Coriolis force is going to act in a direction perpendicular to the velocity. So in the northern hemisphere, we're moving in one direction. It's going to push us to the right, perpendicularly to the right, which is going to cause that velocity vector to veer to the right. And if we're in the southern hemisphere, it acts in a perpendicular direction to the left, which is going to cause that velocity vector to veer to the left. And it's kind of helpful to think of it from the perspective, if we're looking down at the North Pole, then the Earth is rotating in a counterclockwise direction. And that helps us kind of see if the Earth is rotating to the left, then that apparent motion is veering to the right. So, and then if we're in the South Pole, we're looking down at the South Pole. Here we are in the South Pole looking down on the Antarctica continent. That rotation is clockwise, and the apparent motion is going to be that it's going to veer to the left. So in the northern hemisphere, the Coriolis effect creates a deflection to the right. And it doesn't matter which direction you're traveling. If you're traveling from the North Pole to the south or from east to west, it doesn't matter. That deflection is always going to be to the right. And same thing in the South Pole. It doesn't matter which direction you're traveling. That deflection is always going to be to the left. The other important factor of the Coriolis force is the amount of deflection varies depending on the velocity, so the speed of travel, and it also depends on your latitude. So if you're exactly perfectly at the equator, there is no Coriolis effect. There's not going to be any deflection. So if you're moving along the equator, there's no deflection. Now, if you were going to move to the north from the equator, that deflection would go to the right. And if you moved to the south from the equator, that deflection would be to the left. Now, the amount of deflection increases with latitude as we go to the north, and the amount of deflection increases with latitude as we go to the south. So the further away that we are from the equator, the more of an apparent Coriolis force that we have, and also the higher the velocity. So if our wind speed is higher, that Coriolis effect is going to be higher. So remember, at the surface, our wind experiences friction with the Earth's surface, and so that slows the winds down. And as we move up in elevation, our wind speeds increase. And so those upper level winds actually experience a greater Coriolis effect than the winds that are at the surface of the Earth, because they're at lower speeds. So as wind speed increases, the Coriolis deflection increases, and as our distance from the equator increases, either to the North Pole or to the South Pole, that Coriolis effect increases. So it deflects to the right in the northern hemisphere, to the left in the southern hemisphere, and increases with latitude either to the north or the south, and it increases with our velocity.